Welcome to The Explainer. Okay, today we're stepping into a world that honestly feels like it was pulled straight out of a high-stakes spy thriller. But, I assure you, it is very, very real. Imagine, just for a second, that you're tasked with guarding a highly sensitive piece of critical infrastructure. We're talking maybe a power plant, a classified research facility, or a major communications tower. To do this, you deploy a fleet of state-of-the-art surveillance drones to keep watch from above. Sounds pretty secure, right? Well, what if I told you that the very mathematical logic those advanced drones use to fly is actually their biggest vulnerability? Yeah, today we're going to explore some totally fascinating research that proposes using literally chaotic mathematics to make infrastructure surveillance drones completely 100% untrackable.
Okay, let's dive into this, because this is where the conventional wisdom of security basically flips entirely on its head. So, how do you make a security drone completely unpredictable? You see, when we think of robotic efficiency, we almost always think of perfect, predictable loops, right? But if you're an adversary trying to sneak past a security system, predictability is exactly what you're hoping for. Think about it. If a security drone sweeps past a perimeter gate exactly every 4 minutes, well, all a bad actor has to do is wait for minute 4 in 1 second, and boom, they have a wide-open window. Framing these predictable drone sweeps as a massive, highly exploitable security flaw is really the entire foundation of the research we're unpacking today.
So look at standard drone paths. They're essentially just mowing the lawn in the sky. They're predictable, they repeat, and sure, they're super efficient for covering ground. But strategically speaking, they are totally transparent. Now contrast that with chaotic drone paths. These are non-repeating, they fill the space completely, and they are incredibly stealthy. Instead of a boring, trackable sweep, the drone moves erratically. It never ever crosses the exact same point at the exact same time in the exact same sequence. It leaves any potential adversary completely guessing about where that eye in the sky is actually going to be at any given moment.
Section 1. The predictable drone problem. We really need to understand why this is such a critical bottleneck in modern security before we can fully appreciate the absolute genius of the solution.
Look, there's absolutely no denying that unmanned aerial vehicles, or UAVs, have totally revolutionized infrastructure monitoring. I mean, they can inspect the underside of massive bridges, they can map out huge solar farms, they patrol borders, they even have these incredibly advanced algorithms to help them avoid bumping into walls or crashing into other drones. But while those little micro adjustments are really smart, their macro patrol routes, the core loops they're actually programmed to fly, are still fundamentally simple to track. And this simple trajectory tracking remains a really critical flaw in high-stakes security environments.
Moving on to Section 2, meet the Svensson attractor. So how exactly do we program a machine to be intentionally, functionally erratic? Well, it's time to meet the true hero of our spy tech narrative.
Enter the Johnny Svensson attractor. This is a mathematical model that's famous for its complex, unpredictable, and totally non-repeating behavior. Now, don't worry, we're not going to get bogged down in the raw equations here. I just want you to focus purely on how it behaves. This system is ridiculously sensitive to initial conditions. Think of it like the butterfly effect. If you change the starting point of this math model by even the tiniest microscopic fraction, the resulting path it draws out will be completely, radically different. It generates a sequence of points that just wildly diverge from one another. It is fundamentally unguessable, which, as it turns out, is exactly the property we want for a stealthy drone.
And this brilliantly illustrates exactly what we're talking about. When plotted out, we get this 2D Johnny Svensson chaotic point cloud. If you notice those blue points scattered all over the place, that's the raw mathematical output. It's chaotic for sure, but maybe a bit too sprawled out to be practically useful for a drone that's trying to actually patrol a specific area. But notice that compact, dense red core right in the center. The researchers took this completely wild mathematical model and intelligently scaled it down. They basically trapped the chaos inside a defined bounding box. This ensures the drone flies an unpredictable path, but it does so within a tightly controlled, balanced operational zone.
Section 3. Adding the third dimension. Now, the original Johnny Svensson attractor is only two-dimensional. It's flat like a piece of paper. And if you're trying to protect a massive, tall structure like a skyscraper or a wind turbine, flat math just isn't going to cut it. We need to move this into the real 3D world.
This next part is basically the anatomy of an invention. The researchers really had to mold this chaotic math like clay. First up, they added a z-dimension. By integrating sinusoidal functions of the previous x and y coordinates, they basically pulled that flat 2D shape right up into the air, creating actual spatial depth. Second, they scaled down the x dimension to make the whole flight path more compact. And finally, step 3, they integrated a collision avoidance algorithm directly into the trajectory generation. So they aren't just letting a drone fly wild out there, they're very carefully sculpting the chaos.
Let's actually talk about that scaling for a second, because precision absolutely matters here. 0.35. That is the magic number the researchers landed on. By scaling the x dimension down by exactly a factor of 0.35, they perfectly balanced the geometry. Without this specific tweak, the mathematical shape was just way too stretched out on one side to be practical. But multiplying by 0.35 compressed it. It made the chaotic shape compact enough for a physical drone to actually fly it efficiently in the real world, all without losing any of its unpredictable nature.
Section 4, the central void advantage. This brings us to what I think is literally the most brilliant physical feature of this upgraded three-dimensional mathematical model. Because by pulling this math into 3D space, the researchers accidentally, or, hey, maybe intentionally, created the absolute perfect safe zone.
Now, what's really interesting about this slide is the language the researchers used to describe what they actually built. They note that the resulting three-dimensional chaotic attractor resembles an annular cylinder. Okay, let's use a much more fun, relatable analogy here. They basically generated a giant mathematical donut. Yep. By extending the math into 3D, the chaotic flight path forms this thick, dense outer ring of completely unpredictable movement, but it leaves a completely empty, hollow column straight down the middle.
Think of this as the donut defense strategy. It elegantly solves the biggest problem of infrastructure monitoring. How do you intensely patrol a building without accidentally crashing into it? Well, because the mathematical shape naturally acts like an annular cylinder, you just take your vertical infrastructure, the comms tower, the building, and you place it virtually right inside the central void, literally the donut hole. The algorithm forces the drone to fly strictly within the outer chaotic point cloud, meaning the actual pastry body of the donut. The chaotic nature of the math inherently just stops generating any waypoints in that central void. So the drone swarms completely unpredictably all around the structure, but the building itself sits perfectly, completely safe right in the center.
Section 5, proving the unpredictable flight. Okay, all of this sounds amazing on paper, right? Mathematical donuts, stealth swarms, chaotic attractors. But does this actually work outside of a computer simulation? It is time to look at the real-world validation.
The researchers put their chaotic system through some seriously rigorous testing. First, to prove the drone actually covered the whole area and didn't leave blind spots, they used a voxel coverage ratio. This quantitatively verified that the drone filled the bounded volume perfectly. But here is the real spy thriller reveal. To test unpredictability, they used something called an extended Kalman filter. Now you should note the Kalman filter is basically the absolute gold standard predictive tool used in aerospace and security to track moving objects. It is literally designed to guess where a plane or drone will be next. And when they ran it against the chaotic drone, it completely, absolutely failed. The tracking error was massive. Finally, they proved practical feasibility by actually flying these paths on a real Fury micro quadcopter. The complex math translated perfectly to real-world hardware.
So the crucial point is this: you do not need a massive supercomputer to run this incredible stealth security system. The researchers validated this highly complex 3D chaotic math on a simple, low-cost microcontroller designed specifically for power-constrained nano quadcopters. It is incredibly resource efficient. And what this means is that we can deploy highly advanced, mathematically untrackable security swarms using incredibly cheap, everyday off-the-shelf drone hardware. It completely democratizes advanced stealth surveillance.
And that leaves us with a truly fascinating thought to wrap up this explainer. We've just seen how brilliant researchers wrangled the totally unpredictable nature of the Svensson attractor to solve a massive vulnerability in security robotics. And it worked beautifully. So, I leave you with this question. If chaotic math can be harnessed to make a simple, low-cost surveillance drone perfectly untrackable, what other everyday technologies is chaos theory going to revolutionize next? Thank you so much for exploring this wildly fascinating intersection of math and robotics with me today.